In this video, we derive the formula for the VIX. So, as it's on derivation, I need to say that the video is suited for students who want to see why the VIX formula for expected integrating Q volatility has that potentially weird appearing dependence on the cross-section of option prices. The material here is not well suited, in my opinion, for bachelor students nor for business students. On the other hand, it's a good training for industrial engineering and computer science students, and of course math finance students who want to dig deeper into modern financial concepts. As you go through the proof, you will note easily the different assumptions that are necessary to come up with that specific solution. Last not least, if you haven't yet had an introduction into basic stochastic calculus, but you want to understand the flow of arguments, then take whatever you do not understand as a motivation for getting a quick intro into stochastic calculus. Now, suppose the S&P 500 follows an Ito diffusion, which looks as follows, where R is the constant risk-free rate and Q is the constant dividend yield. S is the price of the S&P 500. The term dz is a Brownian motion, and sigma can be any diffusion process for the conditional volatility. We don't need to specify the process for the conditional volatility. Instead, we will use the price on options written on the S&P 500 to back out the expected integrated variance. And last, if not stated otherwise in that video here, every expectation is written under the risk-neutral probability measure Q. Well, I guess you might have known that already, as the expected return of the last stochastic differential equation is simply R minus Q, so absent of any risk premium adjustment. Now first, we apply Ito's lemma to get the density of the log return of the S&P 500. So what we do is we derive the dynamic for the change in the log price, which coincides with that expression here. Now next, remember that I said that sigma can follow any diffusive process. So regardless of which precise process you work with, if you subtract the last equations from each other, you end up with an expression for the instantaneous variance, which itself is simply the Jensen's inequality term. So doing so, you get that equation here, where you isolated sigma square on the left-hand side as a function of ds over s minus the change in the log price. Now let V upper bar be the realized average variance between t in 0 and capital T. Mathematically, that coincides with the time integration of the last equation. Hence, integrating the last equation, we get the following: 1/2 V upper bar times t. It's the integration of the left-hand side rewritten so that V upper bar is the average of realized variance. That's why we also multiplied with t to get the realized variance on the left-hand side. And then we end up on the right-hand side with the integral from 0 to t of ds over s minus the integral of d ln s is simply the log of st divided by s0. Now, in order to be consistent with my intuition video on the VIX squared as the integrated Q variance, I want to define the realized integrated variance as V tilde 0, t, which coincides with t times v upper bar. Now solving for v tilde 0, t gives us the following expression. So taking the expectation as of t equals 0 gives us the expected integrated variance. We hence get that the expected value of v tilde 0t equals 2 times r minus q times t minus 2 times the expectation of log st over s0. So note, the forward spot no arbitrage relation says that the forward price f0t equals the spot price s0 times the exponential of r minus q times t, where f0t is the no arbitrage price on a t maturity forward written on s. So substituting that forward spot relationship into the last expression for the expected integrated variance allows us to rewrite that expected integrated variance as 2 times the log of the futures over the spot price minus 2 times the expectation of the log st over s0. Now here is how we smuggle in the price of put options into that last equation. Just to be precise, all we are now doing in the proof is to take that last equation and get somehow the price of options in. So now look at the following term here. The integral of 1 divided by k square times the max of k minus st or 0 integrated over k, where k goes from 0 to s star for some value of s star. That's now the integral we want to look at for a while. Now that integral is 0 for s star being smaller than s capital T. Make sure you see that. Pause the video if necessary. Now on the other hand, for s star being larger than st, that last integral coincides with the integral of k minus st divided by k square, which we integrate over k for k being going from s capital T to s star. Make sure you see that. And now just solving that deterministic integral leaves us with the log of s star over s capital T plus s capital T over s star minus 1. Now let's do something similar for a different payoff function, namely the payoff function of a call option. Now look at the integral. The max of s capital T minus k or 0 divided by k square, that is integrated over k, and k goes from s star to infinity. Now note that that integral is 0 for s star being larger than s capital T. On the other hand, for s star being smaller than s capital T, the integral takes the following solution. It coincides with the integral of 1 over k square max st minus k or 0 dk from k going to s square to st. That's just the expression, the integrated formula for the call payoff. Now since st is larger than s star, that integral is well defined. Just do the integration. And the reason why I pause for a minute is I still have the max function, but here I see that st is larger than s star, and therefore the max of st minus k and 0, k going from s star to st is always the st minus k. Alright, so therefore that integral should really be just the integral of 1 over k square times st minus k integrated over k, where k goes from s star to s capital T. Solving that integration, you end up with the log of s star over s capital T plus s capital T over s star minus 1. Now, putting the previous two results for the call and the put payoff together tells us that the sum of the put and call payout integrals does for any value of S0 coincide with the log of S star over S capital T plus S capital T over S star minus 1. Now I repeat that here with the math notation. So next, we want to solve that last equation for log of S capital T over S star. So we rearrange that equation and we get to the following equation here, where the log of st over s star is simply st over s star minus 1 minus these two integrals, the put integral and the call integral. So we are now approaching the finale of the proof. Let's take the expectation on both sides of the last equation. We therefore arrive at the following equation here. Now note that we used the insight that the expectation of st under Q can just be rewritten as the forward price due to the future spot parity and from the E2 diffusion of S. Now note that the put of KT and call of KT, these are just my abbreviations for the price of a European put and of a European call on S with a strike of K and a maturity of T. Now, let's get back to our expression for the integrated variance. Now, I repeat the formula here again, as there were so many formulas by now. I want to make sure you know which one we have to look at. So we look at the expectation of V tilde 0t, which we showed above as 2 times the log ratio of the forward price over the spot price minus 2 times the expectation of log S capital T over S0. We now want to substitute the last term on the right hand side with the put-call price equation for the expectation of the log S capital T over S star. Now, what we do is basically now we use a simple accounting trick. We rewrite S capital T over S0 in terms of S capital T over S star. So here's how we do that. The expectation of the log S capital T over S0 can be rewritten as the log of S star over S0 plus the expectation of the log S capital T over S star. Yeah, you see that the S star as a constant would just cancel out. Now we take that accounting trick and plug that into the last 2 equations. Now we therefore arrive that the expected value of V tilde 0t coincides with that following long expression. We have the futures over the spot term, and we have these put and call integrals. Now the term S0 cancels out, so we now arrive at the following expression for the expected value of V tilde 0t. Now that last equation is the expression that the Chicago Board of Exchange uses to determine the value of the VIX squared. To be precise, the CBOE, the Chicago Board of Exchange, discretizes that formula, but otherwise it's the same. So that was quite some work and requires a lot of pausing, I believe, in order to say I've understood all the steps up to here. So that was a workout. Now, as the very last thought, the last equation looks slightly different to the expression that I showed in my intuition video on the VIX as the market's forecast for volatility. Yet in fact, both expressions are the same. I want to show you why. We can choose for S star any value, any positive value. So if you fix S star to coincide with the price of the forward, meaning S0 is defined here to be F0, capital T, then the last equation for the expected value of V tilde 0t simplifies to the following expression, which is just 2 times the exponential of the risk-free rate times t times 2 integrals. One is the weighted integrated put price, and the other one is the integrated call price on the underlying. So note that last equation is the integrated expected Q variance on S, where we here assumed S is the S&P 500 for the time horizon of today up to maturity capital T. So the square root of the average of this expression would then coincide with the value for the CBOE VIX. So the VIX would be defined to be the square root of the expected value of V tilde 0t divided by capital T. And the CBOE uses this last formula to compute its value for the VIX. That Q forecast of volatility is an average of current put and call prices. As each put is weighted by 1 divided by the strike level to the power of 2, you see that out of the money puts obtain a larger weight in the cross-sectional aggregation than in the money puts. For the aggregation of calls, it's in the money calls that get overweighted relative to out of the money calls. Now that tells you that the VIX is sensitive to left tail risk in the S&P 500. To be precise, to the priced in left tail risk in the S&P 500. So therefore, when the press talks about the VIX being a fear index, that is justified, because the fear, which is in the tails, is overweighted in the calculation of the VIX.